In this week's lesson, we'll be talking about the oscilloscope and the use of oscilloscopes in graphing multimeters. The oscilloscope, or slangily called a scope, is basically just a digital voltmeter. Okay, so we talked about voltmeters last time and how we can measure voltage. An oscilloscope just presents that voltage in a graphical type pattern. For example, so on any graph, we've got an x-axis and a y-axis. I should make an R. Okay, so this is what you're going to look at on the face of the scope. Now, this scope will be divided in different scales or grid lines, which are called graticals. On a lot of scopes, you'll see these graticals like so and so, like this. Kind of corresponds to the dividing lines on the axes, and they'll also go up, so that you'll have a dividing line here on this axis. Well, you might see something on the y-axis, for example, and the y-axis is where you'll see, depending on what you're measuring, voltage, resistance, or amperage. And on this x-axis, you'll see time. Okay, whether that's 1 second or 1 millisecond or 1 microsecond. Okay, so basically, let's say that we wanted to look at well, we'll say 100. We'll say on the x-axis we set this thing up to measure 100 milliseconds per division, and the scope has several different things we can use, several different divisions. So I can change that time base to be 1 millisecond per division. You know, it's all just on how I set this thing up. So if I'm looking at 100 milliseconds per division, right here I'm looking at 100 milliseconds. Okay, 200 milliseconds, 300 milliseconds, and so forth. Alright, now I think we need to go back and refresh your memory on milli. What's that mean? 1 millisecond is equal to 1/1000th of a second. So imagine me having a second in time. We'll say that's the. Now imagine me dividing that second into 1,000 parts, and then taking one of those parts. So you're talking about a very, very small amount of time. Okay, so if you take 1,000 milliseconds, that's going to be equal to 1 second. Okay, so if I look at this, what I'm seeing is 700 milliseconds is equal to 7/10 of a second. So we're not quite looking at a full second here, are we? Okay, so let's say I set this side up over here in a common measurement here for what we're going to do here. Let's say we set it up at 5 volts per division. What's that mean? Well, that means I got 0 volts here, 5 volts here, 10 volts here, and 15 volts here. Okay, so now I've got this thing set up, and let's say I put it across the battery, and I touch the black lead of the scope to battery negative and the red lead to battery positive. This is what I will see. It'll actually be a little bit straighter than that. Let me try again. Okay, what you'll see? You'll see that over that entire 7/10 of a second, the voltage stayed at 12 volts. And you basically just see that represented graphically. Okay, but let's say it didn't. Let's say that you had something going on that this thing was constantly being toggled off and on. You'll see an ignition coil works like this. And this is basically all we can do as far as the ignition coil is concerned. And these should be straight and square. You'll be looking at 12 volts, 0 volts, 12 volts, 0 volts, 12 volts. So now this is why you call a DC pattern a square wave pattern. Okay? Because it doesn't vary in voltage like this, per se, like AC voltage would. It's on or it's off. And we also call that a digital signal. Okay? So you could change your base on this. If you change it to 10 volts per division, your pattern would just get a little smaller. So see how changing this time base to 10 volts per division just shrinks that pattern, because now we used to have 10, well actually it should be 12 volts, so it should be a little bit higher. But we used to have 5 volts per division, which put 12 up here, which gave you a great big pattern, something to look at. So you can imagine what would happen, say if I changed it to 2 volts per division. Well, that would move 12 volts on up here, and I get a great old big pattern. Okay, so I can play around with my voltage base here and change how big or how small that pattern is. Same thing I can do with my time base. If I change this to 200 milliseconds per division, these things become wider. Okay, I hope that makes sense, and it probably will as you continue to use the voltage, the oscilloscope. This stuff you can also read over on page 129. The oscilloscope and the oscilloscope display grid is what I'm talking about right here. So let's move on. You've probably seen analog scopes use cathode ray tubes like a television or old school computer monitor. Okay, these analog scopes were big, bulky. Well, some of them were smaller, but they were still big in comparison to a digital storage oscilloscope, DSO. Okay, so it's just two different types of setup. I kind of compare it to a LCD computer monitor compared to a CRT computer monitor. Page 130 gives you some good examples of how to set up voltage to measure different items: fuel injectors, throttle position sensors, oxygen sensors. This is some stuff we're going to talk about more in engine performance. But you know, it's important that you understand that all these things can be measured electrically, and we will be doing that electrically. But for example, a fuel injector, it's a good idea to set that up at 2 milliseconds per division. Okay, so most scopes will have an 8x10 display, which means that you'll have 10 graticles this way. And I didn't draw my screen big enough to show it, but if I had 10, I could measure a complete second, because I'd be out here at 800, 900, and then 1000 milliseconds. So we say we got 10 graticles this way, we'd have 8 going up, and we call that an 8x10 display. We're capable of displaying 8 different voltage divisions, 10 different time divisions. A common question you'll be asked on the test is this. Okay, on an oscilloscope, the y-axis represents voltage. The x-axis represents what? Well, let's go back and look. We do see the y-axis representing voltage. What does the x-axis represent? Milliseconds. We said it might represent seconds. We said it might represent nanoseconds. But regardless of what it's representing, you can always answer that question correctly by saying this: the x-axis represents time. X-axis represents voltage. The x-axis always represents time on an oscilloscope. So let's make sure we don't miss that one. we really hadn't talked much about throttle position sensors, so I don't want to confuse you too much, but basically a throttle position sensor will vary voltage from 0 volts to 5 volts depending on where your throttle is. Throttle position sensor usually runs about a half a volt at idle and about over 4.5 volts at wide open throttle. So what you're seeing on an analog scope is you're watching this line rise and fall as that throttle position sensor opens. Okay, a digital scope is going to look a little different, and you can see this, that it displays from the time you open the throttle to the time you close the throttle again. It tells you the minimum voltage, 680 millivolts or 0.68 volts. The maximum was 4.72 volts, and you see that graphically represented. Alright, what's the advantage of having this scope? Couldn't I see that with a meter? Yes and no. You would to some extent. Alright, let's demonstrate what I mean here. How much time are we talking about has elapsed from the time that you opened the throttle to the time that you closed it again? Now we're talking about 100 milliseconds per division. So what we want to look at is, so if I look at this knowing that's 100 milliseconds per division, what I'm looking at from the time I open that throttle right here to the time I close that throttle right here, I'm looking at 100, 200, 300 milliseconds and a little bit more, maybe let's say about 325 milliseconds as an estimate. Okay, so I'm looking at 325 milliseconds that happened in, or said another way, 0.325 seconds. Okay, in that amount of time, if I had a scope, my eyes can't see that quickly. So if I had a short in the middle of a winding there and this thing went back to 0 like this, that would represent a bad pattern. But over that period of about 25 milliseconds, if you had a scope and you were running this very slowly, you might miss that point and never see that spike. Okay, so a scope helps you see things that happened over a time period that you may not have been able to focus on right when that time period was occurring. To give you another example, let's say that you came into a room and the lights were on. You left the room, you came back in 2 minutes later, and the lights were still on. Can you conclude from that the lights were on the entire 2 minutes? No. Somebody could have come in there and flipped the lights on and off 100 times, but you only had a sample of those two places in time, so you concluded falsely that the light was on the entire time. Okay. If we had a scope connected to it, it would kind of monitor that or make a movie of it. Let's say the scope was like a video camera. I could put a video camera up in the room and I could leave and come back in and I could watch the video and I would say, oh no, the lights didn't stay on the whole time. They were flickering on and off. Somebody was turning them off and on. I can see it because now I'm watching the video, which is kind of acting visually as my scope does electrically. So that's what we're seeing, and we see here that the y-axis represents voltage, the x-axis represents times. We talked about graticals. We talked about the scope having 8 grids vertically and 10 grids horizontally. Most scopes. Some have more, some have less, but that's typically what you're going to find is an 8x10 display. Okay. We talked about setting the time base, right? We talked about divisions. Each gradical is a division. And you can set up how many volts you want per division on the y-axis and how much time you want per division on the x-axis. Okay, the vertical scale has 8 divisions. So it's saying if I set this up to 1 volt and I've got only 8 divisions, the maximum that scope is going to show, and I run out of space, I got to write on your words, is 8. That's the maximum because we only have 8 divisions. So if we set it up on 1 volt per division, we're looking at 8 total volts we can display. Okay, likewise if I set it up at 5 volts per division, we're looking at 40 total volts. Okay, because you got 8 divisions, so that'd be 5, 10, 15, 20, 25, and so on up to 40. Two things we're going to talk about now is AC and DC coupling. Now, DC coupling, the most used position on the scope, allows you to see AC and DC signals present in the circuit. Imagine you got a automotive battery and an alternator. We know the alternator can produce some amounts of alternating current, although it should be rectified into DC current. Okay, so as I look at a DC coupled scope, what I may see on this timeline would be the AC portion of the circuit, which is a sine wave. That's why you see AC voltage represented like this, and the DC voltage as well. So you would see both, and that would be DC. The sine wave would be AC. Now, the difference in that and AC coupling is if you had strictly AC coupling, you would only see the AC signal, and they come in handy for different measurements and different components. And again, that's stuff that we'll talk about more as we go through this course, and hopefully as you continue on in the next course, Advanced Automotive Electricity. There's a lot of stuff we can teach you about electricity, and there's a lot of stuff that that will help make you a lot of money. You know, there's a lot of people that just don't know this information, and we've come so far in this in teaching this that we hope you can feel confident diagnosing electrical problems after you leave this program. Alright, now the AC coupling. When the AC coupling position is selected, a capacitor is placed into the meter lead circuit. It blocks all the DC voltage signals but allows the AC portion to pass and be displayed, and that's what I was talking about with the AC coupling position. You only see the AC portion. One place we use this is to check the ripple voltage to see if any diodes are burnt out in the alternator. Okay, a diode changes alternating current into direct current. So in order for the alternator produces alternating current, but for the battery to use it, it has to be converted into DC current. Okay, we usually do this using 6 diodes. If any one of those burns out, it allows some of this AC current to remain unchanged. So we could use the AC coupling feature to see how much ripple voltage we have and see if it's above spec. If it is, we know that something's wrong with one of these diodes. Alright, the next thing we're going to talk about is pulse width modulation, or pulse train. Okay, and how we can use the oscilloscope to see this.